What happens if you fall into a black hole? Not just any black hole, the kind that swallows stars and laughs at light itself.
I am Richard Feynman, and today I shall show you black holes through my eyes. By the end, you won't sit just know what they are. You still feel them, and understand why quantum mechanics and gravity are in a cosmic dance.
Most people know I won a Nobel Prize, but fewer know I spent more time figuring out how to think than memorizing formulas. That curiosity brought me from dismantling radios as a kid to exploring the edges of black holes in thought experiments. Stick with me. I will make the universe make sense, even where physics seems impossible. You'll still laugh, marvel, and maybe even get dizzy as time and space twist before your eyes. I love seeing the invisible. Diagrams, mental experiments, tiny particles, cosmic giants, all are part of the same story. And black holes, they are the ultimate playground for curiosity-driven science. Imagine space as a trampoline. A star collapses into a point smaller than an atom. Gravity stretches the fabric until nothing, not even light, can escape. That, my friends, is a black hole. But here sits the spine-tingling part, the edge, the event horizon. Cross it, and reality itself starts playing tricks. Time slows, space bends, and if you fall in, well, you once sits be sending postcards back. Now let's talk quantum mechanics. The universe isn't set to just stars, it's set to particles, energy, and probability. Every electron, photon, and quark has its own story. My Feynman diagrams make these interactions simple, even near a black hole. Particles popping in and out of existence, light bending around invisible funnels, time stretching impossibly. That sips the playground of physics. That sips the world I want you to see. Here's something most people never hear: time near a black hole slows. An observer far away sees someone falling in a frozen state for centuries, and tiny particles escape as Hawking radiation, proving the universe has tricks even at its darkest corners. And it sits not magic. These are principles we can understand. Feynman diagrams, probabilities, curiosity, all tools that make sense of the impossible, from quantum particles to black hole mysteries.
Curiosity is everything. Asking the right questions reveals truths that textbooks often overlook. I didn't just win the Nobel Prize because I solved equations. I won it because I refused to settle for half answers.
By the end of this video, you won't just know black hole facts, you will understand them. You will see quantum mechanics as a tool to explore reality, not as abstract symbols. Welcome to Feynman Flux, the place where we break down the universe into digestible, fascinating, sometimes shocking insights. Physics is an adventure here, not a lecture. If you want to see black holes through the eyes of a Nobel-winning physics genius, understand quantum mechanics without the headaches, and embrace curiosity the way I did. Subscribe now. This journey is just beginning. Tighten your mental seatbelt. We start about to explore black holes, quantum mechanics, and the universe itself through curiosity, imagination, and a little mischief. Ready? Let's dive in.
Black holes. The very phrase makes people squirm. Mysterious, dark, inescapable. But here's the thing. They're not some science fiction horror story. They're real. They're extreme. And they're fascinating. And the way I like to look at them, the way I explain physics, is simple, visual, and sometimes a little mischievous. I'm Richard Feynman, and today we're going to explore the cosmic unknown together: black holes, quantum mechanics, and the universe's quirks.
Now let me tell you a little secret about myself, something most people don't know. I had a habit of taking things apart: radios, clocks, anything with gears or wires. I wasn't trying to break them, I just needed to know how they worked. That curiosity didn't stop when I grew up. It propelled me through physics, led me to the Manhattan Project, and eventually to a Nobel Prize in quantum electrodynamics. Curiosity isn't just a childhood quirk, it's a tool. And it's the same tool we'll use to understand black holes today. But before we get lost in cosmic funnels and space-time, let's talk about some of the fun stuff. People know me for physics, but did you know I was also a safecracker? I love figuring out mechanical puzzles just for the thrill of it. And I played the bongo drums, often sitting on a porch in New Mexico, drumming while thinking about quantum mechanics. Curiosity isn't tidy. It spills over into everything you do. And that's what makes learning physics exciting. You're allowed to explore, to question, to laugh at what seems impossible. Now about black holes. Picture space as a vast, stretchy fabric. Put a heavy object on it like a star, and the fabric dips. Now imagine that star collapsing into a point so dense, so heavy that the fabric plunges into a funnel deeper than anything you can imagine. That's your black hole. It's a cosmic vacuum, a place where gravity goes wild, so extreme that not even light can escape. And here's the thrilling question: what happens to light and time near the edge, the event horizon? That's the part of the universe that teases your imagination and defies common sense. We can visualize it in simple ways, and that's the key. Physics doesn't have to be equations floating in a vacuum. It's about making pictures in your head, diagrams that help you see what's going on. That's why I love Feynman diagrams. They're little sketches that tell the story of particle interactions. Imagine them dancing near a black hole, particles appearing and disappearing in ways that seem impossible. And sometimes a particle can escape, almost magically, as Hawking radiation. That's the universe whispering its secrets, and with the right tools, even the most extreme regions become understandable. Black holes aren't just cosmic drains, they're quantum laboratories. And with curiosity, you can explore them without leaving your chair. Now here's a fun visual trick. Imagine an astronaut falling into a black hole. From their perspective, time flows normally, but to a distant observer, they appear frozen at the edge. Space stretches. If they're unlucky, spaghettification occurs, the stretching of matter into long, thin shapes, and light itself bends in ways that turn the simplest beam into a cosmic kaleidoscope. These aren't just textbook facts, they're vivid, almost story-like experiences. And the beauty of physics is that these bizarre phenomena can be explained, predicted, and even understood intuitively. I want you to picture this too: tiny particles constantly popping in and out of existence around the event horizon. Some get sucked in, others escape as Hawking radiation. That's quantum mechanics at work. The rules aren't arbitrary. They're beautiful, consistent, and full of surprises. And the same principles that explain particle behavior here on Earth help us understand the universe's most extreme objects. The universe is like a giant puzzle, and curiosity is your key to unlocking it. Let me take you back to my early days. I was always curious, always tinkering. I once spent an entire summer trying to understand why radios worked. I didn't care about grades or recognition. I cared about knowing. That drive, that curiosity, is exactly what you need to explore black holes, quantum physics, and the cosmic unknown. It's about asking questions that no one else has thought to ask and refusing to settle for half answers. And trust me, when it comes to black holes, curiosity is mandatory. The universe doesn't hand out clear instructions. You have to dive in, imagine, visualize, and sometimes make mistakes along the way. Here's something that often surprises people. Black holes are not just destructive. They're laboratories for the universe. Extreme gravity pushes matter and energy to their limits. Quantum effects become observable on cosmic scales. Time slows, space curves, light bends. Everything behaves in ways that make you question your assumption. And that's exactly why studying them is so rewarding. Physics, explained simply, doesn't mean physics is easy. It means you can see the mechanisms at work without being overwhelmed. And here's where Feynman diagrams come back in. You can draw interactions between particles near a black hole. Imagine the exchange of energy, the popping in and out of virtual particles, and suddenly a black hole isn't a black mystery anymore. It's a playground for the mind. You can predict behavior, see consequences, and even marvel at how the universe allows the smallest particles and the largest stars to obey the same fundamental rules. That's the thrill of physics, the reason I fell in love with it, and the reason I want you to experience it too.
Let's not forget the fun, bizarre, almost playful side of black holes. Imagine light orbiting a black hole in endless loops, or a star being stretched and twisted into a spaghetti-like form. Imagine standing at the edge, seeing the universe age differently around you. It's dramatic, almost theatrical, and yet it all obeys precise, elegant physics. The more you understand, the more stunning it becomes. And all of it is accessible if you let curiosity guide you.
The secret, the one thing I want you to remember is this: curiosity wins. Relentless questioning, the kind I practiced as a kid, taking apart radios or cracking safes for fun, is what lets you tackle the cosmic unknown. It's what makes learning physics, even quantum mechanics and black holes, thrilling instead of intimidating. You don't need to memorize every equation. You need to ask, visualize, and explore. That's the Feynman way, and it works from the tiniest particle to the most massive black hole. So here we are, on the edge of the universe's deepest mysteries, armed with nothing but imagination, a few diagrams, and relentless curiosity. Black holes aren't just points in space. They're invitations to think differently, to see time, space, and energy in ways that challenge your intuition. And quantum mechanics isn't just theory. It's a story, a tool, and a window into the behavior of the cosmos at its most extreme. Think about this next time you look at the night sky. Somewhere out there, gravity is bending light, stretching time, and playing tricks that seem impossible. And with the right mindset, curiosity, imagination, and a willingness to visualize the unseen, you can understand it just like I've tried to understand it for decades. You don't need a PhD, you need a mind that's willing to wander, question, and play. That's the kind of science that makes the universe not just knowable, but astonishingly fun.
Black holes. People look at me and say, Feynman, they're impossible. You can't understand them. And I say, yes, you can. They're just objects in space with extreme gravity, and with the right curiosity and the right mental tools, you can picture them, understand them, and even play with their concepts in your mind. I'm Richard Feynman, and today I want to take you on a journey where black holes become simple, fascinating, and full of surprises.
Let me start with a little story about myself. I was a kid who took apart radios. I didn't know why. I just had to see how they worked. That curiosity never left me. Later, it brought me to the Manhattan Project, to quantum electrodynamics, to a Nobel Prize in physics. I didn't just memorize equations. I explored them. I visualized them. I asked questions no one else thought to ask. That same curiosity is the key to understanding black holes, and that's what we'll do together. Now, you might be thinking, Feynman, black holes? That's way above my head. But let me assure you, they are simple in the right frame of mind. Imagine space as a stretchy fabric. Place a heavy object, a star on it. The fabric dips. Gravity pulls objects into the dip. Now imagine that star collapsing into a point so dense, so heavy, that the dip turns into a funnel deeper than anything you can imagine. That's your black hole, a cosmic vacuum, a place where gravity is so strong that not even light can escape. But here's the first question to hook your imagination. What happens if you cross the event horizon? That's the boundary of no return. Outside, time ticks normally. Inside, well, let's just say normal intuition doesn't work there. Time stretches, space bends. Light curves in ways that make your head spin. And yet it all follows physics. Nothing violates the laws of the universe. It's extreme, yes. Mind-bending, yes. But understandable if you're curious enough to picture it. Let me tell you about another fun side of my life. People know I won the Nobel Prize, worked on quantum electrodynamics and lectured at Caltech. But few know I cracked safes for fun, or that I played the bongo drums, often while thinking about particles and energy. Physics is playful. You experiment. You imagine you sometimes break things just to see how they tick. And black holes? They're playgrounds for that same kind of thinking. Now let's dive into the black hole itself. You have your event horizon, the point of no return. Gravity is extreme. Mass is concentrated into a tiny point called a singularity. Light, traveling at 300,000 kilometers per second, can't escape once it crosses that line. And yet, quantum mechanics adds a twist. Particles can appear, disappear, or sometimes escape as Hawking radiation. The universe isn't cruel. It's clever. And if you use Feynman diagrams, you can visualize these interactions. Lines, loops, arrows, energy exchange. Suddenly, the impossible becomes understandable. Here's where it gets fun. Imagine a particle pair forming near the event horizon. One falls in, one escapes. That escaping particle carries energy away. That's Hawking radiation. Simple in principle, but mind-blowing in practice. This is why black holes aren't just cosmic drains. They're laboratories for quantum physics. And with curiosity, even the most extreme phenomena are accessible.
Let's talk about time. Time slows near a black hole. Imagine falling toward the event horizon. From your perspective, seconds tick normally. But to a distant observer, you seem to freeze, suspended on the edge of space and time. And matter? If you fall in, tidal forces stretch you. Spaghettification is what we call it. Long, thin, stretched. Terrifying? Maybe. Fascinating? Absolutely. Physics explained simply reveals these wonders in ways that intuition alone can't reach.
And light itself behaves strangely. It bends, wraps around the black hole, or orbits it in photon rings. A beam of light can circle the black hole multiple times before escaping, or not escaping at all. These visual effects are not just imagination. They are predictions of general relativity, confirmed by the Event Horizon Telescope. And the same quantum rules you see in my diagrams govern the particle behavior near these extreme objects. Everything is connected.
Let's go back to Feynman diagrams for a moment. They're not just abstract scribbles, they're stories. Imagine drawing a line for a particle, an arrow for energy, a loop for interaction. Now place that near the edge of a black hole. Particles pop in and out. Energy exchanges. Some particles vanish, some escape. You can see how energy moves, how quantum rules operate. This makes black holes less mysterious. They become something you can think about, predict, and visualize, without ever touching one.
You know, when I was a student, I didn't care much for rote learning. I cared about understanding. I'd sit for hours thinking about why a particle does what it does, how electrons interact, and why light behaves the way it does. That curiosity, that playful exploration is exactly what you need to grasp black holes. It's about asking questions, imagining possibilities, and not being afraid of getting the answer wrong at first. That's science. That's learning physics the Feynman way. Now, here's a surprising fact. Black holes shrink very slowly over time. Hawking radiation causes them to lose mass. Tiny, tiny particles escape, and over incredibly long periods, the black hole can evaporate. That's quantum mechanics meeting gravity in a spectacular cosmic dance. And here's the beauty. You can picture it. You don't need years of equations to understand that energy can escape a region where not even light can leave. All it takes is curiosity and visualization. Let's consider another human scale analogy. Imagine falling into a black hole while the universe around you continues to age. Seconds for you are years for the distant observer. You see stars freeze, planets pause, light bends and twists. It's dramatic, almost theatrical, yet predictable. And this predictability, guided by quantum mechanics and relativity, is what allows us to study black holes in thought experiments without ever stepping near one. Curiosity drives everything. I once spent the summer trying to understand radios from the inside out. I didn't care about tests or grades. I wanted knowledge, understanding. That same drive lets you visualize black holes, Feynman diagrams, and quantum particle behavior. Physics is not about memorizing symbols. It's about thinking, imagining, and predicting. And black holes are the ultimate test of that ability. Let's explore Hawking radiation a little more. Near the event horizon, virtual particle pairs form. One falls in, one escapes. The escaping particle carries energy away from the black hole. It's subtle, elegant, and counterintuitive. Yet it follows quantum laws. And here's the important part. You can understand it visually, using simple diagrams. Feynman made complex ideas visual and simple, and black holes are a perfect playground for this approach. Time dilation, spaghettification, photon rings, these aren't just words, they're experiences you can picture. Imagine your body stretching, light bending around you, time freezing outside, and particles appearing in loops around the edge. That's the universe behaving in ways you wouldn't believe if you didn't study it. Physics explained simply isn't about dumbing things down. It's about seeing the invisible patterns, the hidden dance of matter and energy, and enjoying the show. Now let's talk about learning. My approach, the one that won me a Nobel Prize, is curiosity-driven. I didn't just lecture. I told stories. I used analogies. I made diagrams. That's why students remembered my lectures. And that's why you can understand black holes. Don't memorize, visualize, ask questions. Imagine the universe is a vast experiment. Every black hole, every particle, every photon is an opportunity to see physics in action. And there's another trick. Don't be afraid to be playful. I played bongos, cracked safes, and experimented in ways that seemed unrelated to physics. And that playfulness sharpened my mind. Black holes might seem terrifying, but they're playgrounds. You can explore their extremes, visualize particle interactions, and imagine energy escaping without fear. Curiosity and imagination are the only tools you need. Consider light near a black hole. It bends, it wraps around, it can orbit in photon spheres. A distant observer might see distorted images of the background universe stretched and twisted. But if you use your mind, you can picture it. You can imagine what an observer would see, what an infalling astronaut would experience. This is the kind of thinking that transforms impossible concepts into understandable ones. That's physics made simple.
Let me remind you, the same rules govern the tiny and the massive. The quantum mechanics of particles applies near a black hole, even though gravity is extreme. Energy, probability, Feynman diagrams, they still tell the story. And with curiosity, you can trace these interactions, see the energy flow, and imagine the particles' paths. Suddenly, black holes aren't distant, frightening objects. They're laboratories for understanding the universe.
That's the lesson here. Curiosity wins. Relentless questioning, imagination, and visualization let you grasp things that seem impossible. You don't need a PhD to understand black holes, Feynman diagrams, or quantum particle behavior. You need a curious mind willing to ask, imagine, and explore. And if you practice that, the universe opens up in ways most people never see. So imagine the universe as a giant puzzle. Each black hole a piece, each particle an element. Visualize, diagram, think in loops and lines, and suddenly the impossible becomes simple. That's how I approach physics. That's how you could approach black holes. And that's why studying them isn't scary. It's exhilarating. Now picture a particle escaping a black hole's edge. Tiny, energetic, carrying information and energy. Imagine photons wrapping around, stretching, bending. Imagine yourself falling in, time slowing outside. Imagine understanding all of it, seeing it in diagrams and predicting it with logic and imagination. That's physics. That's curiosity. That's learning like a physicist. That's the Feynman way. So, what did we learn today? Richard Feynman didn't just study physics. He made it alive, curious, and even fun. From black holes to quantum mechanics, he showed us how to see the universe with fresh eyes, ask bold questions, and never stop exploring. His way of thinking reminds us that science isn't just about equations. It's about understanding, wonder, and a little bit of play. If you enjoyed diving into Feynman's world and seeing physics made simple, make sure to like this video, drop a comment with your favorite Feynman insight, and subscribe to Feynman Flux for more mind-opening ideas. There's a whole universe of stories, experiments, and discoveries waiting for you, so don't stop here. Click through our other videos and let your curiosity run wild. Keep thinking, keep exploring, and let Feynman's spirit guide your journey through science.